Hello students, in this video lecture I am going to discuss join and meet of the empty subset of a PO set and the join and meet of a PO set or a partially ordered set. So for discussing the join and meet of these two particular subsets, that is the empty subset of a partially ordered set and the partially ordered set itself, let me consider P less than equal to be a PO set and let S contained in P be a subset of P. Then what we are interested in finding out is that we are interested in finding out the join of S and the meet of S, or the V of S and the inverted V of S when S is a subset of P. In particular, S can be the set P itself, or S can be the empty set phi, or the empty set is even denoted by the set with curly brackets. So for these two particular extreme cases, we are going to find out what is the join of S and what is the meet of S. So although as far as the definitions of the join of S and meet of S are concerned, where S is any subset of P, these two definitions we have already discussed in my earlier videos. So they have been discussed in detail along with the relevant examples. But for the sake of this video, let me just discuss or let me just recall rather these two definitions again. What do we mean by join of S and what do we mean by the meet of S, where S is any subset of P. Now, as far as join of S is concerned or Vs is concerned, then Vs or join of S stands for the supremum of S or the least upper bound of S, provided the supremum of S or least upper bound of S exists. What do we mean by least upper bound of S? The least upper bound of S is that upper bound of S which is the least of all upper bounds of S, which means least upper bound of S is that element X belonging to P which is not only an upper bound of S but it is lesser than any other upper bound of S. This is what we mean by the least upper bound of S. So whenever the least upper bound of S exists or the supremum of S exists, supremum is another name for the least upper bound. So whenever the least upper bound of S exists or the supremum of S exists, we say that the join of S exists or Vs exists. So that was the definition of join of S. And coming to the definition of meet of S, recalling the definition of meet of S stands for the infimum of S, or it stands for the greatest lower bound of S, which means that it is that lower bound of S which is greatest of all the lower bounds of S, which means that greatest lower bound of S is that element X belonging to P which is not only a lower bound of S but it is greater than any other lower bound of S. So it is greater than all the lower bounds of S. So if such a element X belonging to P exists which is a lower bound of S and which is greater than all the lower bounds of S, or then we say that the greatest lower bound of S exists or infimum of S exists. Infimum is another name for the greatest lower bound. So so if the greatest lower bound of S exists or the infimum of S exists, we say that the meet of S exists, and the meet of S is denoted by inverted Vs. So these are two notations that, as I said earlier, have been discussed in details in my earlier videos along examples. So if one is interested in knowing more about the join of S and the meet of S, where S is any subset of the PO set P, then one can refer to those videos where these definitions have been given in details. Now coming to what we had to discuss in this particular video. Now we are interested in finding out what is the join of S and what is the meet of S when S in particular is the whole PO set P and S in particular is the empty set phi. So let me consider the first case, which is case 1, when S, the subset of P, is the whole set P. We are interested in finding out the join of S or the join of P, because S in this case is P, or we are interested in, and also we are interested in finding out the meet of S or the meet of P, because S is P in this case. So let me find out both these two things one by one. Now let us suppose that P has a top element T. The top element is denoted by capital T. Again, the top element has been discussed in detail in my earlier videos. So if P has a top element and if you try to draw the hash diagram of P, then the top element T of P will be at the top, and all the elements of P will be lower than that because they will be smaller than T. So by the definition of the top element, all the elements X belonging to P will be less than equal to T because T is the top element, so it is greater than equal to all the elements. So X is less than equal to T for all X belonging to P. This is the definition of the top element, which means that the top element T is acting like an upper bound of P. So this is an upper bound. The top element T, if it exists, it's an upper bound of P. And also we can note from this diagram itself that T is the only element which is acting like an upper bound because all the elements of the PO set P are below T. They are smaller than T. So T is the only element which is greater than equal to all the elements of P, which means that T is the only upper bound of P. Now because T is the only upper bound of P, so if you collect the set of all, if you take the collect all the upper bounds of P, which means that if you consider the set PU, this particular notation was used in my earlier videos. The PU is the set of all upper bounds of P. So if you collect all the upper bounds of P and if you want to find out what are the elements of PU, then we will see that the only element PU will have is T because T is the only upper bound of P. So now so if now we are interested in finding out what is the supremum of P or the least upper bound of P, or what is the least of all upper bounds. Now because there is only one upper bound of P, which is T, so definitely this is the least upper bound also. So this means that the least upper bound of P will be the top element of P, which is T, or the join of P will be equal to T because join of P denotes the least upper bound of P or the supremum of P. So whenever P has a top element T, then the join of P will exist and the join of P will be given by T. This particular relation I have marked as 1. So this is one conclusion that we have. Now coming to the second thing, let me find out what is the meet of P. Suppose the PO set P has a bottom element inverted T. Now if P has a bottom element inverted T, then by definition of bottom element, the bottom element inverted T will be less than equal to X for all X belonging to P because inverted T is the bottom element, so it is smallest of all the elements of P, which means that if we try to draw the hash diagram of P, then inverted T will be at the bottom and all the elements of P will be above it or will be greater than equal to it. So by definition, the bottommost element or the bottom element inverted T will be less than equal to X, which means that the bottom element T is acting like a lower bound of P because it is lesser than all the elements of P. And also we can see from the diagram itself, the hash diagram of P, that the inverted T, which is the bottom element, is the only element which is smaller than all the elements of P. So it is the only lower bound of P, and now because it is the only lower bound of P, so definitely it is the greatest of all lower bounds just because it's the only lower bound. So if we collect all the lower bounds of P, which means that if we try to write down what are the elements of PL, PL is the set of all lower bounds of P, then PL consists of only one element, which is the bottom element, which is the inverted T. And since this is the only lower bound of P, as I said earlier, this is the greatest of all lower bounds of P, or this is the infimum of P, or this is the meet of P. So the meet of P is given by the bottom element. So this is another conclusion that we have over here, that the meet of P, which is the greatest lower bound of P, which is the infimum of P, is given by the bottom element T, provided the bottom element of P exists. So there are two conclusions that we have. Now this particular conclusion I have marked as 2. So these are the two conclusions that we have. Just collecting the conclusions together. Whenever P is a PO set, this means whenever P is a PO set, and whenever P has a top element and whenever P has a bottom element, which means the top element, if you draw the hash diagram of P, the top element will be at the top and the bottom element will be at the bottom. So this top element will be the join of P and this bottom element will be the meet of P. So these are two conclusions that we have from here. So this actually gives us a way for calculating the join of P and the meet of P whenever P is given to be some particular PO set. For example, if P is given to be a chain of 3 elements, let's say this is the PO set P, which is a chain of 3 elements, and let's say the elements are marked as A, B and C, then the join of P will be the top element which is at the top, which is C. We can see from the diagram itself, and the meet of P, as we have just seen, the meet of P will be given by the bottom element, which is A, because it is at the bottom. So immediately by looking at the hash diagram, we can just find out whether the PO set P will have a join or not, or it will have a meet or not. So if the PO set P has a top element, as in this case, and it has a bottom element, as in this case, immediately you can conclude that the join of P will exist and the meet of P will exist. So this was one example. A similar example, likewise, if you have let's say another example which I have considered in my earlier videos, the examples which we have been generally taking. So if you take X to be a set consisting of 3 elements, 1 2 3, and if you take P to be the power set of X, then we know that the power set of X, which is the set of all subsets of X with respect to the inclusion relation, this we know is a PO set. And if you try to draw the hash diagram for the power set of X, then we have already seen in detail how the hash diagram of the power set of X looks like. One of the way of drawing the hash diagram is in the form of a cube. So this particular cube represents the hash diagram for the power set of X, where X is the set consisting of 3 elements, 1 2 3. And if we see that at the bottom we have the empty set phi, and at the top we have the whole set X. So just because the hash diagram shows that the power set of X, the hash diagram of power set of X has a bottom element and it has a top element, this means that the join of P will exist and the meet of P will exist, and the join of P will be given by the top element. The top element is X, and the meet of P will be given by the bottom element, which is given by phi. So immediately by looking at the hash diagram of the PO set, we can immediately make out whether the PO set has a join or not, or whether the PO set has a meet or not. So this is how we apply these particular conclusions that we have found out in star. Now coming to case 2. Now case 2 was the other extreme case that we had to discuss, the other particular extreme case that we had to discuss, when the subset S of P in particular is the empty set phi, or the empty set is even denoted by a set with empty curly brackets. In that case, what is the join of S, or what is the join of phi, and in that case, what is the meet of S, or what is the meet of phi. So let me find out the join of S and the meet of S one by one. Now when S is equal to phi, or when S is empty set, let me pick up any element X belonging to P to be any arbitrary element. It's an arbitrarily chosen element of P, but once it has been chosen, we are fixing it at the moment. So take any arbitrary element X belonging to P, then we find that this particular statement, S less than equal to X, for all S belonging to, for all small s belonging to capital S, where capital S is the empty set phi, this particular statement is true vacuously. We say that this statement is true vacuously. Now what do we mean by saying that this statement is true vacuously? Now this particular statement needs an explanation. This particular line needs an explanation. Now if we consider this particular statement, which I have enclosed in a box, this particular statement. Now this particular statement which I am saying is true vacuously, we can rewrite this statement in the form of a implication. Suppose I am rewriting this in the form of an implication. It can be, the statement can be rewritten like this, that for all S in P, where P is the partially ordered set, S belonging to S such that S belongs to S, for all S in P such that S belongs to S, this implies that S is less than equal to X. This I am saying is true vacuously. This is what I am saying. I have just rewritten the statement which I have put in the box, that if S small s is in P, because P is the underlying set, P is the universal set in consideration, P is the set which we are referring to at the moment. So if for all S in P such that S belongs to capital S, where capital S is the set phi, or the empty set, so this will always imply that S is less than equal to X. This is true vacuously. Now this is an equivalent way, this implication, this particular implication, the way I have written this implication, this one, this is an equivalent way of writing this particular statement which is in this box. So they are equivalent, both of them are equivalent ways. Now as far as this implication is concerned, if you regard the first part of the implication, which is S belonging to S, if you call this as statement PS, and if you this second part, S less than equal to X, if you call this as statement QS, then this particular implication which I have just written can again be rewritten as for all S in P such that PS this holds, this implies QS will be there. So PS implies QS. So this is what we have. So this I'm saying is true vacuously. I'm saying that this particular statement is true vacuously. So I have just written this particular statement which is in box in the form of this. In the form of implication, where PS stands for S belongs to capital S, where capital S is phi, and QS stands for S less than equal to X. So for all S in the PO set P, the underlying set PO set P or the universal set P, you have that S belonging to phi implies that S is less than equal to X. I'm saying that this is true vacuously. Why this is true vacuously? Because whenever you have statements which are in the form of implications, like this in mathematics, in logic, or in logic, in mathematics, whenever you have statements which are in this form, in the form of implication, and if you consider the first statement, which is the statement PS, which is called the hypothesis. Now if this hypothesis is false for all S in the underlying set, which is the universal set, in this case the universal set is P. So if PS is false, then this whole implication will be a true statement, or it will be true vacuously. This way of proving things is called a vacuous proof. This is how a vacuous proof is given. This is a technique which is followed in mathematics or in logic, which is like this. I'll explain again, that if you have a statement, which is in the form of implication, the way this particular statement is, it is in the form of an implication, and in this particular statement, which is in the form of implication, if the first statement, which is PS, which is called the hypothesis, if this particular hypothesis is false for all values in the underlying set or the universal set, if it is false, then this whole statement, this whole implication will be a true statement, or it will be true vacuously. So now if you take a look at the statement in our context, the statement which is in our context is this one. Let me write it again. The statement in our context is that for all S in P, for all S in the PO set P, S belonging to the empty set phi implies that S is less than equal to X. This is what we have. This is the implication in our context. Now this is your PS and this is your QS, and I'm saying that this statement is true vacuously because if you take a look at PS is the statement that S belongs to phi. So we can see that for all S, whatever S you choose in P, in the PO set P, this particular statement, which is S belonging to phi, this can never hold. This can never be true because phi is an empty set. An empty set cannot have any element. An empty set, so whatever S belonging to P you may choose, S can never belong to the empty set phi, which means that PS in our context is a false statement, and because PS is a false statement, so this whole implication is true vacuously, or this is a true statement. So what we have given is a vacuous proof of the statement, which we have written in the box. So this particular statement is true vacuously because we have given a vacuous proof of the statement. And what is the vacuous proof of the statement? We have written this particular statement in the form of implication, like this: PS implies QS, and we find that because this particular statement PS is false for all the values of S lying in the underlying set, which is the PO set P. So this particular statement, this whole statement, which is in the form of implication, is true vacuously. And this box, we find that this is in the form of implication, so it is true vacuously. So now once this has been proved that it is true vacuously, this statement tells me that this X, which is an element, which is an arbitrary element of the PO set P, is behaving like an upper bound for the empty set S, So this x belonging to P is because this x is greater than all the elements small s of S. So it is so if you try to draw the hash diagram, this x will be up at a level up. It will be at the upper level, and all the elements of the empty set supposedly will be at a lower level as per this statement. So this means that x is behaving like a upper bound for the empty set S is equal to phi. So x belonging to P is an upper bound for the empty set S, which is equal to phi. But x belonging to P, as we have seen, this was an arbitrarily chosen element. So this means that this particular statement which I have written in the box, this particular statement is true for all elements x belonging to P, which means that every element x belonging to P is acting like an upper bound for the empty set phi, or this means that every element of P is an upper bound for the empty set phi. Or if you collect all the upper bounds of the empty set phi, which means phi u is the set of all upper bounds of phi, then phi u consists of the whole set P. So phi u is equal to P, and if you try to find out the least upper bound of phi, then the least upper bound of phi will be the least element of P, because all the elements of P are upper bounds. So if you want to find out the least upper bound, you should find out the least element of P, and the least element of P is the bottom element of P, and the bottom element of P is denoted by inverted T. So provided it exists. So this means that the least upper bound of phi, or the join of phi, is going to be the bottom element of P, provided the bottom element exists, or the least upper bound of phi is also called the supremum of phi. So supremum of phi, or least upper bound of phi, or the join of phi will be the bottom element of P, which is the inverted T, provided the bottom element exists. Which means that from here we have another conclusion, that another important conclusion that we have from here is that join of phi is equal to the bottom element inverted T, provided the bottom element inverted T exists. So this conclusion we have marked as 3. And now coming to the last case, where I am interested in finding out what is the meet of phi, or what is the greatest lower bound of phi. So if S is equal to phi, let me take x belonging to P to be any arbitrarily chosen element. Then this particular statement, x less than equal to S for all S belonging to S. Again, this particular statement is true vacuously. Why is it true? Because we can give a vacuous proof of this particular statement. I can write this particular statement in the form of implication, and in the form of implication, the same way as we did before. If you write it in the form of implication, you can write it like this: for all S in P, because the underlying set is P, the PO set P, this is the universal set or the underlying set in this case. So for all S in P such that S belongs to S, where capital S is the empty set, whenever S belongs to S, this will always imply that x is less than equal to S. I'm saying that this statement is true vacuously. This is what I'm saying. And why is it true vacuously? Because if you consider this particular implication, then in this particular implication, if you consider the first part, if you regard the first part as PS is S belongs to capital S is phi, and if you regard the second statement, which is x less than equal to S, this as QS, if you regard them like this, then we can see that PS, which is S belonging to phi, this is false for whatever S belonging to P, where P is the underlying set or the universal set in consideration, in our case, in this context. So whatever S belonging to P you may choose, S can never belong to phi. This can never happen. This can never be true. This is always false. Why? Because the set phi, this is empty. This doesn't have any element. So this means that phi cannot have any element. So PS is false. So PS is false for all values of S belonging to P. Now because PS is false, so this particular implication, which is of the form PS implies QS, you can write it like this, where PS is false for all S belonging to the universal set, where the universal set is the set P. So because PS is false, so this whole implication will be true vacuously. This is by the again, this, I repeat, this is by the technique that we have in mathematics for giving a vacuous proof. So by using that technique, we have that this particular implication is true vacuously. So this particular implication is true vacuously, and this particular implication is actually same as this statement, which means that this particular statement is true vacuously. And now if you take a look at this particular statement, then we can see that this x belonging to P, this means that this x is acting like a lower bound, because it is lesser than all the elements of the empty set capital S or empty set phi. So this x is acting like a lower bound. It is smaller than all the elements of S, so it's a lower bound. But x belonging to P was arbitrary chosen element. This means that whatever element x belonging to P you choose, every element x belonging to P will act as a lower bound. So so if you collect the set of, if you try to find out what are all the lower bounds of the empty set, then which means that I try to find out what are the elements of phi L. Phi L is the set of all lower bounds of phi. Then it will consist of the whole set P, because every element of P is acting like a lower bound. So phi L is equal to P. And now if you want to find out what is the greatest of all lower bounds of phi, then greatest of all lower bounds of phi will be the greatest element of P, because all the elements of P are lower bound. So greatest of all lower bounds will be the greatest element of P, and the greatest element of P is definitely the top element of P, which we denote by capital T, provided capital T exists. This means that the greatest lower bound of phi, which is the meet of phi, that is given by the top element of P, which is capital T, provided capital T exists, and the greatest lower bound of phi is also called infimum of phi. So from here we have a conclusion that the meet of phi, or the greatest lower bound of phi, or the infimum of phi, is the top element T, provided the top element exists. This particular conclusion I have marked as 4. So there are 2 more conclusions that we have for the empty set. We have 2 conclusions, that join of phi is the bottom element, and the meet of phi is the top element, provided the bottom element and the top element of the PO set P exist. So 4 conclusions in all we have in this particular article, that if we are interested in finding out the join of P or the meet of P, then the join of P will be given by the top element, the meet of P will be given by the bottom element. And if we are interested in finding out the join of phi and the meet of phi, the join of phi is the opposite of this, which means that it will be the bottom element. Here it's top and here it is bottom, and the meet of phi is the top element T, provided the top element T of P exists, and provided the bottom element inverted T of P exists. So that was all about in this video, in which we have discussed what is the join of the whole set P, the PO set P, what is the meet of the whole set PO set P, what is the join of the empty set, and what is the meet of the empty set.